In the last lecture, we talked about exploration in multi-armed bandit. And specifically, we talk about two algorithms. One is epsilon greedy or epsilon first algorithm. The other one is the upper confidence bound. We're saying the epsilon greedy algorithm, which just naively like try random action at epsilon fraction of the time, while upper confidence bound kind of like combines both exploration and exploitation by computing this upper confidence bound, which is mean plus some bonus. And by looking at that, we're saying we have a better trade-off between exploration versus exploitation. So it turns out in the epsilon greedy, we get a regret, which is t to the 3/4, something like that. And UCB, we get square root t regret. And this is in the multi-armed bandit setting. And today we will talk about the reinforcement learning scenario. So in the reinforcement learning scenario, we noticed the exploration is much challenging than like a multi-armed bandit. Specifically, we talk about we have this counterexample, which is a combinatorial lock, where if we do random exploration or do epsilon greedy, we actually pay something like a to the h, at least exponential in horizon, to first identify what is the optimal arm. And in this case, you can easily prove the regret would be something like either linear in t until like you get the t is greater than a to the h, something like that, a to the omega h. So this is like a really bad. So in terms of in a multi-armed bandit, the only problem of epsilon greedy is just we get a slightly worse regret in terms of rate. But in the reinforcement scenario, we actually ping something exponential in horizon. So this is like not tolerable. So basically, this lecture will talk about how we're going to use the better idea in exploration to incorporate that to reinforcement learning. The idea is basically we just incorporate a UCB into the reinforcement learning, and we will get something like again we will get square root t and a polynomial in h. So this is the algorithm we will talk about. We will just by combining value iteration, which is the algorithm we use for reinforcement learning, with UCB. So let's first talk about the algorithm. So the whole idea is basically very similar to the UCB algorithm in the multi-armed bandit setting. Instead of just looking at the mean, we also add a bonus. So here is similar. We also do the bonus type of algorithm. So the algorithm is called a UCB VI algorithm. It's upper confidence bound value iteration algorithm, which was introduced in Azar et al. 2017. So the algorithm we first initialize with some empty data set. Let's call this D as data set, and let's say it's empty, because when we begin the algorithm, we don't have any data. We haven't observed any trajectory. And we initialize QH SA. I think this is important because we always want to maintain the upper bounds to the optimal value function. So we just initialize it to be H. Okay. Because H is the upper bound, is always an upper bound on the value. Just recall our normalization conditions, like we assume the reward in each step is 0 to 1. So the maximum value you can achieve is capital H. Specifically, it should be like capital H minus little h. Okay, but for here, let's just say capital H. For all SAH. We will also initialize VH plus 1, capital H plus 1, as. This thing is the value at H plus 1 step. We know there's no reward received after H plus 1 step, so this is always equal to 0 for any s. So the main algorithm consists of the following two parts. Again, the exploration setting, we need to say for episodes k from 1 to capital K. So in each episode, we're doing two major steps. The first step is actually we're calculating the UCB of value, upper confidence bound of value at each step. So this is about compute UCB of values the idea is basically just doing value iteration plus bonus. So when we do value iteration, we start from the very last step to the first step. We start from capital H to H minus 1 and till 1. So what we do is we first check if this state action pair if this SAH is already in this data set D. So if in a data set do we have ever observed an SA pair at H step? If so, we can compute this empirical estimate. We again use the empirical average as my estimate. We use the ratio, like how many times we have observed SA S prime pair in the data set, divided by how many times I have observed SA H at H step. Those are counts in data set. So the only difference is like in the simulator setting or generative model setting, we sweep over all the state action pair, so we can guarantee this is like some fixed number. NSA is fixed number. Now, because we're doing exploration, sometimes we might never be able to visit some state action, so that one will be 0, and we will treat it in some other way. Okay. So as long as this is not 0, we can use the empirical average to estimate the transition. And then all we do is we just do the value iteration update, slightly modified. We first do some truncation so that we guarantee the value iteration. The value we got from value iteration will never be greater than H, which is our upper bounds, always an upper bound. And then we just use the Bellman update to do Bellman update and replace the transition P by P hat. And this is a standard value iteration update. So our modification is, in addition to doing this, we also add a bonus. And the bonus will be only as a function of NHSA, as how many times we have observed SA at each step. Okay. So basically this step is, we just do value iteration, but with this P replaced by empirical estimates and adding some bonus, okay, and also doing some truncation. And in the case, if we haven't observed SAH in the data set, basically we won't do this step, and we will just the Q value will be remain as the initialized Q value, which is capital H. So it's still well defined. Q value is well defined. It's just it's not according to this update, but it's just H. So the next step is sorry. Here, Mr. This is saying for all SA. So this is a Bellman update for Q value. So next we will do Bellman update for V value, which is essentially the same for all S in S. We do this VHS equal to max A in A, QHSA. So again, for any SA has already been observed, the Q value is defined in here, and if the SA has not been observed yet, the Q value will be the initialized Q value. So this V value is again also a well-defined thing. So basically this entire part is how we're going to compute the UCB of values. The high-level idea is very simple. It's just we add a bonus to the Q value updates. Okay. And there are other variants for it. Why do we want to have this? Yeah. Because sometimes, like in the very big, we will see later, this bonus is something like 1 over square root of n, and times c times h squared and log term, something like that. So in some case, like when n is not very large, like for example, if we only observe 1 or 2 values, we might add a lot of bonus. And in that case, my Q value will be very large. And Q value very large, it goes down to the next step. We'll talk about like how we construct this bonus. I think the main reason we construct this bonus is like we want this to be an upper bound. And if Q value in the intermediate Q value become very large, and then that will hurt the entire proof on how it becomes an upper bound, because essentially we want to do some concentration. So we will see the reason later, but mostly just so to make sure like this Q value is well controlled. It's not like extremely large, and everything is well behaved in terms of concentration and statistical error. I think this will not happen if we don't add this bonus. Like only this bonus can make this Q like extremely large. So that's why in the earlier step, in the simulator setting, we don't do this truncation. Okay. So this is a part about we just compute the UCB. But after we consider UCB, and the other step in the multi-arm bandit is we will take greedy action regarding to the like upper confidence bound we computed. In the multi-arm bandit setting is basically we computed upper confidence bound for each arm, and we just take the arm that has highest upper confidence bound. Here is essentially the same. We will just take greedy action regarding to this Q value we computed. So for H, from 1 to H, we will take action. AH is equal to argmax A in A, QH SHA. Okay. And we will observe the next data and next states. SH plus 1 and the reward RH. And then we just add this tuple to the data set. D is equal to D union with a new tuple. That is, at H step, we observe SH AH and SH plus 1. So the second part is essentially execute greedy policy. So you can think this is just like reinforcement MDP version of a UCB algorithm. Instead of like adding bonus to the value of each arm, you're adding bonus to in the Bellman update. So that to compute the upper bound of Q value, and then you just take a greedy policy regarding to this upper bound of Q value. Any questions?
Sorry, what is that D again?
D is the data set. D is this data set.
That's a D, or wait, okay.
Yeah, I think I swapped the vision a little bit. You can think this is if you are rigorous, if there exists any DHSA and it can be anything in D. That basically just says I have ever observed an SA pair at each step in this data set.
Wait, so what is the D of NHSA again? Or that's just like literally.
What? D of H?
Like at the end of that QHSA line, like on the second side of the minimal.
Sorry?
What is that again?
What?
Okay, the bonus. Okay. I see.
Oh, this one?
Yeah.
Yeah, this is our choice of bonus. Yeah, we'll talk about that. So basically, we already mentioned here our choice of bonus. The bonus is only a function of the count, like how many times we observe this SA pair at each step. And this choice will be equal to C, some constant, times square root of H squared iota over N, where this iota is just some log factor, like log SAT over P. So we will actually show why this construction of bonus is valid, and you will see like why this thing kind of like happens. So essentially, this bonus reflects our confidence of this value after seeing it n times. So it somehow reflects the fluctuation. Of random variables bounded by H. Because eventually this is like something random according to the value. Okay. So after we introduce the algorithm, we will now talk about like what kind of guarantees we can provide for this algorithm. First, any question about the algorithm? Algorithm part is just more or less like a time series version of UCB algorithm in the multi-arm bandit. Okay. So because this is like an exploration setting, we will also talk about regret in the MDP. And in the last lecture, we already says like once we get a regret, we can easily convert it to the sample complexity. So regret is even stronger notion. I think in a lot of reinforcement setting, we don't really care about regret, but you can think this is like a convenient way of getting sample complexity as well. So in terms of regret in the MDP, we can also define a regret up to k round is equal to k times the optimal value subtracted by the value we get at every episode. V1 pi k s1. Okay. This is like the total value if we always play optimal policy. This is the value achieved by the learner. Okay. So it's the same definition. The only difference is like replace the reward of each arm by the value of MDP. Okay. So the most important theorem we will say is actually we can show with probability at least 1 minus p the regret of UCB VI algorithm is upper bounded by the following, that regret k is upper bounded by some constant c times the square root of h cube SAT iota plus h cube s square a iota square, where this t is equal to kh. You can think you can also put h to the fourth. So regret up to k round is this amount. So sometimes people write it in t because t is the total number of steps you observe, and k is the number of episodes you observe. Let's see. Where this iota is again the logarithmic term. Okay, usually we don't care, it's just SAT over P. Basically you can think log everything. Log HSAT. I think we can also put an H here. It doesn't really matter. Oh, we already have H. Yeah, I think SAT is fine because T is like a KH, so T is already containing H inside. Okay. So we kind of like notice this is like the formal theorem, but basically if we want to know the like leading order term, this is like square root T term, and this is something independent of T. We know to regret will be something like, the worst case regret will grow like linear in K. So the square root K is already something non-trivial, and this is like something constant independent of K. So this is like the lower order term. This is a leading order term because square root K. This is a lower order term because it's independent of K. So what we really have done is we kind of like achieve this, this guarantee kind of like already says something like that. We get square root T or square root K, but the most important thing is we don't pay anything like exponential in H, as in the random exploration or epsilon greedy, where we basically only pay polynomial in H in the worst case.
like the order of k, right?
Yeah.
Because k is like larger than s.
So the question is, the t term is order of kh. Kt is just exactly equal to kh.
I'm saying like we care about like what the regret is in terms of k. So that's why like this term matters.
Yeah, this term matters. This is the leading term because this is like square root k term. So now we'll talk a little bit more about like why this algorithm would work. Like we intuitively say this is just adding bonus similar to UCB. So we'll actually be a bit more concrete in proving theorem 1. So in order to do that, we will introduce a bit more notation so that we don't confuse with a quantity. I think the most important notation is like we will add this superscript k. The reason is here we kind of like repeatedly we update Q value based on the new data, and it kind of like a little bit confusing if we just say some Q value because at each different episode the Q value is actually different. So we're just adding a superscript k to denote the quantity computed at episode k. Okay. For example, like we have NHK SAS prime. Okay. So essentially in the algorithm we have this NHSA, but here like to be very specific about which episode, like the number is showing up in which episode, we will like to add a superscript k here, and this will be denoted as a number of HSAS prime observed up to episode k. Okay. And similarly, we will also use the pk hat HS prime SA, denoted the empirical transition matrix we computed at the case episodes, and the Q value at case episode, V value at case episode. Essentially, we will just denote those notation. These are the values. And finally, we will say this SHK, AHK, or we will say S1K, A1K, till S capital HK, A capital HK. This is the trajectory collected at episode K. By the way, I forgot to mention that there's one thing we need to be careful. Like in the value iteration, it turns out in the episodic setting, we only do one pass of value iteration. But here in the exploration setting, we notice at every episode, we're collecting one new trajectory. And after collecting one new trajectory, we do a full path of value iteration. This is essentially like we recompute a value iteration path at every episode. So this can be like costly in the end. And we will talk about another algorithm queuing later because of this. This requires compute a full path of VI at every episode. So this is like very costly because at every episode we only observe one trajectory. However, we're kind of like updating all the values. We're updating all the values because it can relate it to like the value in a later step can be updated. So we need to recompute everything, and this is like very costly. Yes.
What's the word over there? Compute also
For paths of VI. For paths of VI. Sorry. Okay. So with this new notation, essentially the way we're going to prove theorem 1 is very similar to the UCB in the multi-arm bandit setting. We essentially have two steps. One is we will show that QKH SA is an upper bound of Q star HSA. Okay. So this is by the name of UCB. Essentially, the way we construct, we design this bonus, we want to ensure this is true. And the second step is we do the regret analysis. And by UCB, we will eventually able to show something like a regret is smaller than summation of all the bonus. And this is what we have been done for the UCB setting in the multi-arm bandit, like up to some constant. And here we will do something after small terms. So the second step is a little bit tedious for this a lot of computation in the for the lectures. So we will leave the second step to lecture notes. If you're interested, you can look at a specific calculation about how to derive the regret bound. So in the class, we will mostly focus on the first step, showcase why our construction justify this is an upper bound. So we will do this in lecture. Do this today. And this will defer to lecture notes. Okay. So formally, for the first step, we need to prove the lemma. Essentially, this is we just make this statement more rigorous. This step more rigorous. We say with probability greater or equal to 1 minus p, we have QHK SA greater than Q star SA, and VHKS greater than VH star S for any SAHK in set of state, set of action, and horizon is upper bounded by h, and this episode is upper bounded by capital K. So basically, throughout at every step and throughout all episodes, we will always maintain with high probability this our computed Q value will always be in the upper bounds of the value of the optimal policy. Any questions about the statement before we proceed to the proof? So essentially, the proof a lot of times of reinforcement learning is basically by induction. So here again, we will do the induction. We will do induction from capital H to 1. So the base case is for the h+1 step. Because in the algorithm, we never update the value at h+1 step, so this is not updated. So that means at every episode, my value at h+1 step will be always equal to the initial value we set, which is equal to 0 and equal to the optimal value. Okay. So the base case is pretty straightforward. Okay. So now we assume we have VH+1 K as greater or equal to V star H+1 S for all S. That is, for all the later steps, we already guarantee this VH+1 K is already the upper bound of V star. So now we want to do the induction to prove for each step we still have the value is also in upper bounds. So we divide it into two cases. The first case is if state action HSA is not in decay. So that is this HSA pair has not been observed in the data set up to case time. So in this case, we haven't updated. QHKSA, because if we don't observe it and we basically skipped update, so it will be still remain as a initial value. So this QKHSA will be equal to the H, which is initial value, which is clearly in the upper bounds of Q star HSA. And on the other hand, if we have observed this, and then we kind of divide it into two steps, divide it into two cases. if we already know H is less or equal to RH SA plus what do we have? Like essentially the P hat H SA P hat VH plus 1K SA and plus bonus. In this case, because we're doing the truncation, we we know the Q value will be equal to H. Because remember in update, we're doing the minimum of the two. This is equal to H, and it's again greater than Q star H, SA. So the only non-trivial case is the otherwise, like this is actually smaller than H. So the last case, we need to do a little bit calculation. This is basically the reason why we pick this specific choice of bonus. So we look at the QK HSA, subtract by Q star HSA. This we can basically by the update equation, we immediately know this QK by definition is equal to P hat HK, VH plus 1K SA, and plus bonus. And then subtracted by second part, which is by Bellman equation. PH, VH plus 1 star, SA. So essentially, we just expand this, use update equation, expand this, use Bellman equation, and then we cancel out the reward. So we can rearrange the term a little bit. We say this is equal to P hat HK, VH plus 1K, subtracted by VH plus 1 star, SA, plus P hat KH, subtracted by PH, VH plus 1 star, SA, and finally I'm adding the bonus of B of NHK, SA. Okay. So all I'm doing is we subtract this P hat V star and add the P hat V star back. So I didn't do anything. It's just we kind of decompose the difference into two parts. The most important reason we decompose those terms into two parts is we can basically conclude the first term is greater or equal to 0 by induction. So by induction, we know this is equal to 0, greater or equal to 0. Because we know for any step in the future, like H plus 1, we already assume this is already an upper bound. So once this VK is an upper bound of V star, and if you just apply some transition on something positive, this is again a positive thing. So this will be immediately greater or equal to 0. This is fine. So in order to make this QK to be an upper bound, all we need to make sure is the second term. We want to ensure the second term greater or equal to 0. And now we become very familiar with this thing because essentially what we want to do is we use a bonus term to cover some like a stochastic term, which turns out this is like a summation of independent random, maybe not independent random, but like summation of martingale terms. And eventually we can say as long as we use some Hofding bound to do this. So to more specifically, we can say Hofding's inequality guarantees with probability at least 1 minus p for all KHSA. We have the following, that is this PKH hat subtract by PH VH plus 1 star SA. So this P V star is the expectation, while this P hat V star is the empirical average of K of like a NHK independent martingale samples. So we can say this is less or equal to C times H squared iota, where H squared is essentially the scaling of V. So we know this is like bounded by H. C times H squared iota of NHK SA. Okay. So this is just by Hofding inequality. Essentially, we have this many items, summation together, with taking an average, and we know the convergence is like 1 over square root of n. So this is why we put a 1 over square root of n here. And we specifically choose it so that we match the bonus. Essentially, we make the bonus to be exactly equal to this, or maybe greater than this by some constant factor, and this is, yes?
So is this like a martingale like using a Zuma Hofding, or it's just?
I think this is essentially the same thing we talk about in the UCB scenario. Like if you still remember in the UCB scenario, we also need to, like in the multi-bandit case, we also need to do this type of concentration. We're saying this is essentially a Hofding inequality. With the only difference that this NHK, like the number of times you pull that arm, here is also the number of times you visit the SA. K is like random. So that's why you you need to do a little bit more advanced techniques in addition to just the Hofding. You need to like do Azuma Hofding, which is the same like a similar argument to UCB. To handle the randomness. In this count, NHKSA. Okay. So this essentially justified our choice of bonus, and we can essentially just put a bonus here, and we say like this will, with high probability, cover whatever the negativity happens in this like concentration term, and so we can guarantee this is greater or equal to 0. And that finished the proof. Okay. There is actually one more step. So. So the very last step is very, very fast. So once we prove this QHK SA is greater or equal to Q star HSA for all HSA, we just say the v value is also the same. This implies that VHK SA is equal to the max over A Q HK SA. And this is greater or equal to, we're taking max over lower bound, that is Q star HSA, which is equal to VH star S. So essentially, we can use this to finish the induction, and everything is done. As we say, eventually the proof of theorem 1 will be just some regret analysis, because we already proved the upper bound, and then we can essentially leverage this fact to show that regret k is less or equal to summation of the bonus, or specifically is something like k from 1 and h of this bonus at nk, nhk, shk, ahk. So we will only count in the bonus at the state action we visited at the case episode, and plus some small terms, some other small concentration terms. So we'll leave this to lecture notes. But I just want to emphasize, like, this is usually the way we prove the upper bound, like UCB algorithm. First, we prove it's upper bound, and then we say regret is upper bounded by bonus. So we can see from here, we cannot just, if we only care about the first part, being upper bound, we can just make bonus to be extremely large. Like, for example, I always pick Q value to be capital H. And that's clearly an upper bound. But the problem is eventually the regret is going to be bounded by some constant times the bonus. So in that kind of case, if we make the upper bound very loose, this bonus is also very loose. And this entire regret will suffer a lot. So essentially the key point here is like we want to make this upper bound as sharp as possible. So in this case, we essentially use the concentration inequality to do the upper bounds. And then eventually we can do the regret based on this.
QK upper bounding Q star. Why does that, like, how does that relate to the upper bounding bonus?
Upper bounding bonus? Sorry.
So in theorem, in lemma 1, we just proved that QK is upper bounding Q star.
Right.
And then, like, how does that relate to?
So I'm saying for the lemma 1, we can actually choose bonus to be very large.
Oh.
So for example, in here, all we say is like, as long as we choose bonus greater than this Hoffman concentration, we can actually guarantee this to be an upper bound, right? So basically, we can choose any bonus that's greater than this. So that won't hurt the lemma 1, but that will hurt the second step where we prove the regret, because regret is upper bounded by the bonus. So that's why we want the sharpest bonus as we can. So another thing I want to talk about is design of bonus function. So it turns out this UCB VI algorithm, the design of the bonus function actually matters because this bonus function actually not only affects analysis but also affects the algorithm. Because in the algorithm, we explicitly need to add a bonus to the value, and then we collect data according to the greedy policy computed by this upper bound on the value. So this design of bonus function actually affects the algorithm and the data we collect. Or trajectory we collect. So this is why it goes back to the previous point I said. We want to essentially use the sharpest bonus function we want, but on the other hand, it's still computable. It doesn't depend on some uncomputable quantity. So the way we introduce the lecture, this Bn is equal to h squared iota c over n. This is what we previously did. This is essentially designed by Hofstad's concentration inequality. So as we learn from the concentration inequality, we actually know this is Hofstad's concentration inequality is not the sharpest concentration inequality. A lot of times we can actually do Princeton's inequality, and that's actually give a sharper bound. So it turns out you can also design and improve the sharper bonus based on Princeton inequality. So presumably this is going to help. So the only complication here is because Princeton inequality actually depends on the variance, where the variance, which is different from Hofstad, which is essentially just it's a bounded random variable. We know it's bounded by h, so we just directly put an h here. Well, here we essentially need to estimate the variance. So this creates a lot more, a little bit more steps because we essentially we don't know the variance, so we need to estimate the variance and use the estimated variance into our a bonus design, and the analysis is a lot more involved. But eventually, if we make everything work, you can actually improve a square root h factor. In regret. So what I mean is actually doing a sharper bonus indeed gonna help in terms of a regret. So originally we get some square root h to the h cube SAT, and now we get a square root h squared SAT. So any question up to now? So after we introduce the entire UCB VI algorithm, we want to revisit the hard instance we talk about, which kind of make it very difficult to exploration, the combinatorial log. Why UCB is able to solve this problem. if you still remember, combinatorial lock is a two-state MDP, where essentially there's only one specific action sequence that eventually going to reach the end state, that S0. Everything else is going to lead to the absorbing state S1. And never goes back. So we say if we just do some random exploration, this problem actually is very difficult because the chance we sample precise action sequence that A1 star, A2 star, A3 star till AH star is like exponentially small. And it's extremely difficult to find this optimal policy by just doing some random exploration. However, we can see by doing UCB, it's actually doing a lot better in a sense, like it eliminates incorrect action very fast. So we will essentially start with all the value to be like H, all the Q value to be H. So after we observe some multiple trajectories, for example, at this step, if we observe a lot of other actions, like in addition, which is different than A3, we notice this Q value of other actions that is not A3 will like decrease very fast. So it will goes to 0 like very, very fast. So in that case, we'll eventually very fast eliminate the incorrect action. We'll like do this step by step, and eventually we will be able to find this optimal value like in some polynomial time. So actually So essentially the whole idea is, again, we will do the dynamic programming type of way to find the optimal policy. Okay, so this also says the combinatorial lock thing is actually only hard for specific algorithm, like for random exploration. It's actually not very hard for well-designed algorithm. For example, for VIUCB, we can actually guarantee this one will not suffer from some exponential H. And it's actually, with polynomial time, we can already find the optimal policy.
Okay, so the reason why it decreases is because like, when you traverse the incorrect path, then that increases the sample of that, so that the bonus goes up.
Right. Okay. So this is about how we're going to combine the upper confidence bound idea with the value iteration. So remember, in a simulator setting, we not only talk about the value iteration, we also talk about Q-learning algorithm, which is doing incremental update. And we also notice in the VIUCB setting, we notice that there's one very big computational problem. Like in every episode, we need to do a full path of value iteration. Although we only like observe one trajectory, but we need to do the entire path. So essentially, we will see. Actually, we can do the Q-learning with UCB as well, and this algorithm will actually fix that computational issue and be the truly online learning algorithm. So the algorithm is as follows. And this is in our previous paper. in 2018. So again, we initialize all the Q values to BH. And NHSA equal to 0. That is the count for all HSA. So we do the for loop. That is for episode. K from 1 to capital K. We first receive first state, initial state S1. And then for a step, H equal to 1 to capital H. So we no longer decompose the entire thing into two big chunks, like the VI or collecting data. So the benefit of Q-learning is like we do incremental update. So every time we collect one new data, we will immediately do the update. So we kind of like combine the taking trajectory with this value update. So we'll take action, AH is equal to argmax. A of the current value we maintain, and observe the next state. And we will set some t is equal to count of SHAH, which will be incremented by 1 because we observe this SHAH now. So this SHAH is always the count, how many times we have observed this SHAH at each step. So the most important part is we do this Q value update. So this QH, SA, SHAH. If you still remember, and the Q value is, Q-learning update is equal to 1 minus alpha t fraction of the previous Q value, QH, SHAH, plus the alpha t fraction of the new value. Alpha t fraction of the update, where update is equal to the reward and plus the value of the next step taken on the states we observe in the current data, and plus a bonus, B, where B is only depends on this t. So again, we just add in this bonus. Where we choose this bonus is equal to C times, with slightly worse dependence on H iota, H cube iota over T. And then we just do the V value is equal to the max of Q value, but truncated with H. That's it. So we see this, there's no need to compute the p hat, which is the estimate of transition, where in this entire Q-learning, we don't actually compute p hat. So this is typically considered as a model-free algorithm. And also, we only update the value on trajectory revisited. So instead of doing a full pass of value iteration, which will need to essentially recompute the value for all state action and h at every step, here we only update the value at the state and action we visited. So this is a lot faster in computation than VIUCB. And also remember, we have this like a memory advantage. So again, key thing here is we need to essentially put more. Remember, in the Q-learning, one very important thing is doing like this bias variance trade-off. So we need to put more weights on later updates to like reduce the variance, which kind of like, if you still remember in the simulator setting, which is equivalent to like choosing this learning rate alpha t is something of order h over t. Okay. So we noted if it's chosen as 1 over t, this is exactly equal to like a uniform average. Well, now I'm like putting it greater than 1 over t, so that means I put more weights on the like later updates than the previous updates. So once we do this, everything like that, we will essentially be able to prove the next theorem with probability greater or equal to 1 minus p, the regret of Q-learning UCB. Is at most less or equal to c times square root of h to the 4th SAT iota, where iota is again a log term. And we also notice this regret is 1 square root h factor worse than UCB VI. This is due to the same reason, like this is like incremental updates. Similar in the simulator, in a generator model, like simulator setting, we also observe a slightly worse sample complexity because we essentially need to favor the later updates so that we're not handling noise as good as like a VI UCB, which is like basically remembering all the data and use the smallest like variance. here's online updates, and we kind of like throwing away data, so we're less efficient in terms of sample complexity than the UCB VI. Okay, I think we're gonna stop here today. So starting from next lecture, we're gonna summarize this exploration setting and then start talking about lower bound. Yes, questions?
I was wondering, you said there's less weight on the later updates, but alpha T is decreasing, or there's more weight on the later updates, but alpha T is decreasing with T, so isn't there less weight on like what's getting added later on?
So alpha T is always need to be decreasing because you have more and more samples. So even if you're doing uniform weight, you should expect alpha T to be decreasing because like if you have T data, every data only get a weight 1/T. If you had like 2T data, every data should only have like weight 1/2T. That's the uniform. So I think in the last lecture, the lecture before, we kind of like we explicitly mentioned if this is a 1/T, and by doing this 1 minus alpha T of fraction of previous one and alpha T fraction of the new update, you get precisely uniform average. And whatever you make it greater than 1/T, then it's like a favoring later one than the previous one.
How can Q-learning be faster to compute than UCBVI, but also less sample efficient?
So the fast to compute in terms of per iteration, it's per episode is much faster to compute. But the less sample efficient means like it probably need slightly more episodes.
So, but overall, then would UCBQ learning be slower if you want to?
Will not, because this is only like a square root of h factor worse in terms of sample capacity. So that means essentially you need h more factor like of episodes. But per episode, you are only like computing one trajectory, like updated one trajectory. While in the UCB VI, you're essentially doing a full path evaluation that you need to look at all states and all actions. So there, essentially, you have a SA factor more in terms of computation. So there's a trade-off there. And in the next lecture, we'll actually talk about that trade-off.